Okay. Good evening, everybody. I hope all of you are in complete health and everything is going well for all of you. Okay. Unfortunately, a few students have come to class and we cannot wait any longer, and we should start. Please let me continue the chapter because it has not finished yet. And after finishing the chapter, I'm going to give more example. I'm going to give more examples and to solve and do some practice together for better understanding. So, because we have not enough time, at first let me start the remaining last chapter, and then we will discuss more about that. As a review, please let me explain a little about the chapter that we discussed together last week. If you remember, we started a chapter, namely SPC, or Statistical Process Control. I told you there are two types of variable or variation, natural and specific. I told you in process of production or service, there are some variations. Some of them are natural and we cannot do anything, but some of them are specific or assigned problem. In this type of variation, please let me back to slide number 4. In assignable variation or another or special causes of variation, I told you there is a problem. This problem can be due to labor or machinery and something like this, and in this situation we should look for the problem and try to solve it. So we should stop the process to prevent more defaults. So in process of production or service, if you see the process is going wrong and there is something wrong there, we should stop the process and look for the problem. How we can understand the problem, the process is not under control? I told you there are some methods that can help operation managers by which monitor the process. The most important step in this method is sampling. So operation managers should do sampling and select some sample randomly and take them to laboratory and measure them or test them, and by analysis of the data, they can understand the process is under control or not. What was the method? If you remember, I told you the method was the control chart. So the control charts are tools that can be used by operation managers that by use of them, they can monitor the process and understand what's going on. So as I told you, the first method was X bar chart. There were some variables in this chart that should be calculated. The most important one was UCL or upper control limit and LCL. There is a formula for calculating them. X bar bar plus Z sigma X bar and LCL equal X bar bar minus Z sigma X bar. As I told you, the Z and sigma can be determined by engineers or top managers, and they are given to you. So the operation manager can calculate X bar bar and other variables. I gave you an example, and I told you, for example, one operation manager in a company which is producing oat flakes. In other one, go to production line and choose sample by use of 9 cups. He or she randomly selected 9 cups of the oat flakes and take them to laboratory and measure their weight. As I told you, the important variable that should be monitored or that should be measured by operation manager is weight. So X or variable in this example was weight. X is the variable. The weight of each cup was measured by operation manager, and they wrote the data and their result on a table on the left, hour 1. When they measured the weight of the 9 cups of oat flakes, then they calculated the mean of these 9 cups of oat flakes. The mean of these 9 cups of flakes give you X bar, or average of the weight of sample. But in the formula, we need X bar bar. So in each hour, we should do the same sampling and then measure the mean in each hour, and finally we should calculate average of average, or X bar bar. X bar bar gives you average of average. If you remember, I told you in 12 times operation managers did sampling, and in each hour or in each time they calculated mean of 9 cups of oat flakes. At the end, they should calculate the measure of this mean. The average of this mean. The average of this mean in table on right gives you X bar bar. If you sum up these 12 numbers together and divide it by 12, it gives you X bar bar. UCL or upper control limit that is very important for X bar chart can be calculated now. X bar was plus Z sigma X bar. If you remember, I told you there is a formula for sigma and its X bar. It's radical sigma divided by radical n. N is sample size. Here the sample size is 9 because operation managers select 9 cups. So the sample size is 9. The radical sigma. Sigma is given to you by engineers or top managers as much as 1. Radical sigma or radical 1 divided by radical n or radical 9 gives you 1/3. 1 on 3. 1 on 3 multiply 3 because z is given to you equal to 3. Plus 16. 16 is X bar or mean of X bar, average of X bar. You can calculate UCL and LCL through this formula easily. After calculating UCL and LCL, we should draw the chart as you can see in the screen. UCL is 17, LCL is 15. Each bar or is the middle, exactly in the middle of these two lines, in the middle of the UCL and LCL, as you see. In each hour or in each sampling time, you calculated X bar. You should determine each X bar in each hour according to table on the right. Look at the table on the right, hour and mean, hour and mean. Hour 1, mean of the 9 cup was 16.1. Hour 2, 16.8. You should bring this number to this chart. Hour 1 on the horizontal axis is 16.1 that has been determined by blue spot. Hour 2 of 16.8 is near to 17 as you see. All of these blue spots are a pair of the numbers, hour or sample time and X bar. When you determine this blue and when you see the LCL, when you draw the LCL and UCL are two horizontal lines that cross the vertical axis in box 15 and 17. The allowed area has been determined by color. All of the blue spots should be fall in this allowed area between LCL and UCL. But as you see, 3 spots have fallen out of this area. Number 10, number 11, number 12. Because in hour 10, the mean or X bar was 14.8. Look at the table on the right. In the hour 1 is 14.8. It's less than 15. Because we told you the LCL or lower control limit or minimum control limit is 15. The number below 15 is not acceptable, and the number above 17 is not acceptable. But in the hour 12, the mean were 17.3. It's more than 17. So the process is not under control, and there is a assignable variation or a specific variation. Operation manager should stop the process and look for the reason of this problem. I told you, if you don't know sigma, and if the sigma is not given to you, there is another method for calculating LCL and UCL. X bar bar plus A and is 2 multiply R bar, X bar bar minus A and is 2 multiply R bar. R is average range of the sample, R bar. A and 2 can be determined in table, and X bar bar is mean of the sample mean, or average of sample average. This is a standard chart here that has been given to you. You should, by use of the sample size, you should choose the A and is 2. The name of A and is 2 is mean factor. In another example, I gave you the process average or X bar bar 12 ounce, average range R bar is 0.25, sample size N equal 5. Sample size is N equal 5. From table, N equal 5 in sample size gives you mean factor of the 0.577. Sample size is 5, so A and is 2, or mean factor is 0.577, as you see in the table. When you replace these numbers with variable in the formula, we can calculate UCL and LCL easily. I gave you this example without any background. I gave you quickly only the last data. Okay, LCL is 11.857, UCL is 12.144, mean is 12. You should take the data over and mean of each other to this chart, and then all of them has fall inside the allowed area or not. Allowed area means between UCL and LCL. All of the spots, blue spots, should be fallen inside this area between UCL and LCL. R chart. The second method is R chart. R means range. R means range. If you remember, I told you the definition of range. Range is the the difference between maximum and minimum number in each sampling. For example, in our one or in sample number one, other one and sample number one means the both of them are the same. In the sample number one or in other one, we had 9 number because we have 9 cup of outflows. The biggest number, the maximum number in this sampling or in this hour was 18, and the minimum number was 13. The difference between 18 and 13 equal to 5, because 18 minus 13 gives you 5 or produce 5. So the range in R1 is 5. R1 is 5. R2 can be calculated exactly the same as this. In R3, or we can calculate R3, range 3. In other 4, we can calculate R4, exactly the same. We had R1, R2, R3, R4, R5, and finally R12. We have 12 R. We have 12 range. If you sum up this range together and divide it by 12, it gives you R bar. R bar means average of range. R bar means average of range. It means that in each hour we calculated one range for that hour. For example, in hour one, the range or R1 was 5, because in hour one the difference between maximum number and minimum number was 5. And also we had a range for hour 2, we had a range for hour 3. This range are R1, R2, R3. When you sum up this 12 number and divide it by 12, it gives you R1. Okay, it's the second type or another type of variables control chart. Shows sample ranges over time, difference between the smallest and largest value in sample. Monitors process variability independent from process mean. In the R chart, for calculating upper control limit or UCL and lower control limit LCL, we have this formula. D and is 4 multiply R bar, and D and is 3 multiply R bar. R bar is average range of the sample, as I told you. D3 and D4 should be brought to this formula to the table, this table. Based on the sample size, you can calculate D4 and D3. Upper range and lower range. D4 is upper range and D3 is called the lower range. For example, in one company, average range or R bar have been calculated like this. R bar equals 5.3 pounds. Sample size is N equals 5. From table, N equals 5 gives you N equals 5. We want to calculate D4 and D3. From table, N equals 5. N equals 5 gives you D4 is 2.115 and D3 is 0. Okay, everything is clear. Okay, let's continue. UCL equals D4 multiply R bar. D4 from table was 2.115 multiply 5.3, that is R bar, gives you 11.2. D3 was 0, so LCL is 0. LCL is on horizontal axis. Okay, we calculated LCL and UCL, and you can brought the S-path line here. But In the R chart or range chart, the horizontal axis is sampling, is number of sampling, is number of hour, for example, 12 hour or 12 sampling time. And vertical axis is range. For example, in hour 1, the range was 5. You should bring 5 and hour 1 as a spot together. In hour 2, the R2, for example, is 8. In hour 3, the range or R3 is 5, 6, for example. This number should be brought in this table, in this chart, sorry. All of the spots should be located between LCL and UCL. If one of the spots is out of this area, process is not under control. It was our chart. Now we want to summarize the steps in creating control charts. Number 1. Take samples from the population and compute the appropriate sample statistic. Number 2. Use the sample statistic to calculate control limits, LCL and UCL, and draw the control chart. Number 3. Plot sample results on the control chart and determine the state of the process, in or out of control. Number 4. Investigate possible assignable causes and take any indicated actions. And number 5. Continue sampling from the process and rest the control limit when necessary. And reset the control limit when necessary. These steps are used in creating control charts. Sample statistic means sample data. For example, its weight, temperature, and something like this should be calculated, should be measured, temperature, speed, weight. Because in each production, one variable is important. In the oat production, the weight is important for company. But it may you work in another company that temperature is important for you. So you should control the temperature. Sometimes you should control speed. You should control length. And something like this. Okay. Control charts for attributes. Do you remember what was the difference between attributes and variable? Anybody know? What was the difference between attributes and variables? I told you last week. If anybody wants to talk, please let me know to free his or her microphone. So all of you have forgotten? What's the difference between attribute and variable? Anybody know? No. I told you variable is can be measured directly by tools. For example, weight can be measured by a scale. Meter and temperature meter. They can or temperature can be measured by temperature meter. They are the variable. But attributes cannot be measured directly. We should calculate them through another way. For example, the level of hard working for a person. There is no tool that can help you to measure the level of hard working for a person. Good, bad, acceptable, unacceptable, yes, no, all of them are attributes. We can compare them together. For example, a person that has achieved A plus for mathematics is more hardworking than a person that has achieved C plus. The hardworking cannot be measured directly, so it's attribute, not variable. But temperature, width, length, height, and something like this, pressure are variable because they can be directly measured by tools. Measurement is typically counting defective. Charts may measure percent defective, number of defects. Okay. In this, if you remember, I told you there are four charts, four control charts. I explain you two control charts. Now, two charts have remained, P chart and C chart. P chart and C chart usually involve the attributes, because in this chart we don't calculate anything. I mean that we don't calculate the average and mean. We involve the number of defective products. We don't. It's different with each bar chart and R chart. Let me explain you will understand better. For example, in P chart, population will be a binomial distribution, but applying the central limit theorem allows us to assume a normal distribution for the sample statistics. It means that in some company, the number of defective products should be measured. Here we involve the number of defective products. For example, imagine you are producing fan. Fan, as you know, is a tool that can be used for hot weather in summer to cool you. Company is producing 200 fans per hour, per each hour. In each hour, the operation manager test all of the fans, and they understand For example, 10 fans out of 200 fans in our one have problem. They are defective. In our two, they test, for example, the fan and they see 5 out of 100 or 200 is defective, has problem. They calculate the number of defective in each hour. In this chart, we can calculate UCL and LCL through this formula. P bar plus Z sigma P and LCL P equals P bar minus Z and multiply sigma P. Sigma and this P. P bar is equal mean fraction defective in the sample. Mean fraction defective. Fraction defective means you should divide the number of defective by the number of production. For example, when you are producing 200 fans per year and 10 divided by 200 gives you fraction defective in other one. Z is the same as the R chart, number of standard deviation. Is a statistical variable. Sigma P is a standard deviation of the sampling and N is sample size. Sigma P, as you see, can be calculated by root square or radical P bar multiplied by 1 divided by N. It gives you sigma. Okay, so in the P chart, it involves the non-defective and fraction defective. Non-defective in each sampling divided by number of sampling or number of production can give you P fraction defective or not. And also the deviation sampling or sigma P can be calculated through this formula. Radical P bar multiplied 1 minus P bar divided by N. Okay, so in the P chart, we involve the number of defective and fraction defective. For example, imagine in a company, operation manager has done 20 sampling or in other one or in, for example, in sample number 1, the number of errors or number of defective products was 6. The sample size is 100. N equal 100. It means that in each sample number or in each hour, 100 products has been selected operation manager. In sample number 1 or hour 1, the number of errors, number of defective 100 gives you 0.6. That gives you defective. In sample number 2, the number of error, number of defective 5. 5 divided by 100 gives you 0.05. It is defective or P1, P2. P was 0 because the number of errors was 0. In number 4, only one product was defective. So the fraction defective P so is 0.01. Finally, in the sample number 20, the number of errors was 4. Fraction defective is 0.05. 0.04. The whole number of defective, total number of defective is 80 for all 20 over or for all 20 sample number. When you sum up the number of errors, number of defective, it gives you 80. This is the number of total number of defective in whole 20 hours or in whole sampling. P bar can be calculated as the number of whole defective divided by whole production or whole sample size. The number of defective was 80. 80 divided by we did 20 sampling, and each sampling we select 100 unit product. So 100 multiplied 20 gives you 2000. It means that the number of defectives in 2000 products was 80. In whole 2000 products, the number of defectives was 80. 80 divided by 2000 gives you 0.04. This is P bar. Sigma P, if you remember, it has a formula, radical P bar multiply 1 minus P bar divided by N or sample size. P bar, we calculated P bar. So the P bar can be calculated as the number of defectives divided by total sample size for whole sampling. Sigma P equal to 0.02. Okay, so P bar and sigma P can be calculated through this data table that has been measured by operation manager. UCL and LCL can be calculated easily by formula P bar plus Z sigma P bar, sigma P is equal 0.1 and LCL is equal to 0 according to Python formula. Horizontal axis is sample number or number of hours that was 20, and vertical axis is fraction defective. For example, in sample number 1, the fraction defective was 0.06, if you remember. All of this data from the table, for example, sample number 1, fraction defective was 0.06. Sample number 2, fraction defective was 0.05. Sample number 3 was 0 until end. Okay, you should bring this data to this chart. This is P chart. Vertical axis is fraction defective, shows fraction, and horizontal axis shows sample number. Okay, The process is under control or not under control. Who wants to talk and analyze these charts? According to this P chart, the process is under control or not under control. It's very easy. UCL and LCL has been calculated and has been drawn in this chart. Do you hear me? Okay. Based on this chart, is under control or not under control? All of the blue spots, all of blue dots have fallen inside. Please look at the chart. Please look at the chart. All of the spots have fallen between UCL and LCL or not. All of the blue spots or blue dots have fallen inside the area or not. It's not under control because sample number 16, one of the blue spots or one of the spots is the sample number 16. It has fallen outside. It's more than 0.1. It's more than UCL. So the process is not under control. Okay, do you understand? That's under control. Why that's under control? Some students believe it's under control. Why? Okay, I told you. Even one point has fallen outside, the process is not under control. Even one. As you see, the sample number 16. In sample number 16, please let me check the table. Number 16. In sample number 16 over 16, yes, the fraction defective is, sample number 17. Sample number 17, the fraction defective is 0.11, 0.11. It's more than UCL because UCL is 0.10, but we have 0.11. This is outside. This is more than UCL. One of the number 17. So the process is not under control. I told you, even one point fall outside the area, you should tell the process is not under control. Because be sure you will face problems in future. So it's better you stop the process and look for the reason. Please look at chart and UCL and CL. 1 minute and concentrate on them and think about that. Okay. Possible assignment pauses present. It has determined by yellow box. Yes, exactly. Even one point is not UCL or LCL, the process is out of control. And the fourth chart, the last chart is C chart. In the C chart, we involve like P chart. As I told you, in P chart and C chart, the number of defectives is important for us. But in R chart and X bar chart, we should have measured variables. For example, weight, temperature, and something like this. In the C chart, also the number of defectives should be determined by operation manager, and by this formula, UCL and LCL should be calculated. UCL equals C bar plus C3 multiply radical C bar, and LCL equals C bar minus 3 radical C bar. What's the meaning of C bar? C bar is the mean number defective in the sampling. Okay, let's look at the formula UCL and LCL. I repeat again. In C chart and P chart, we involve the number of defectives. Imagine, now I want to give an example for service company. Imagine in company that 54 complaints during 9 days. They received 54 complaint letter during 9 days by customers. The complaint letter shows the defective in service company, shows something is wrong. The 54 complaints during 9 days gives you 6 complaints every day. It means that 54 divided by 9 gives you 6. It means they have received 6 complaints per day. It gives you C bar. C bar is the number of defectives divided by sample size or sampling, sample hour. Here the sample day, Effective means complaint letter in service company. The UCA equals C bar plus 3 radical C bar is 6 plus 3 radical 6 is equal to 13.35. It's UCL. Okay. UCL and LCL can be determined by like this, and when you there the chart, the horizontal line is sampling, number of sampling. We have 9 days here, and the number of the effective or number of the complaints should be shown by vertical axis. For example, in day number 1, in day 1, they received 3 complaint letters. In day 2, they received 0. Day 3, they received 8 letters. 4, for example, 9. The sum of these complaint letters become 54. The number of total complaint letters become 54 for 9 days. Okay? Now, we want to see the process is under control or not under control. Okay. Yes, under control. It means that these complaints are natural. You know, even the number of complaints is natural and more than yes. Yes, the sales company. We monitor the process for customers. And in every our service to 500 per day. After 9 days, 500 you 1,000 customers by this company. So, for example, 54 complaints they have received. Give shows that it is understood. But if, for example, the complaint of more than, for example, 500, for example, 600, then we could tell the process is not under control in that time. Managerial issues and control charts. Measure management decisions. Select points in the process that need SPT. Determine the appropriate charting technique. set clear policies and procedures. It means that at first they should select select the variable or select the things that you want to measure, you want to monitor. For example, temperature, speed, number of defective, and something like this. After determining this, you should select the appropriate control chart. If you want to work based on number of defective, you should select P chart or C chart. And if you want to measure one variable such as temperature, weight, and something like this, you should select X bar chart or R chart to monitor the process. And after that, after monitoring the process and analyzing data, you should set clear policies and procedures. For example, to solve problem and something like this. Which control chart to use? Variable data. As I told you for many times, using an X bar chart and R chart, observation are variable, collect 20-25 sample of n equal or n equal 4, 5 or more, select samples of n observation each. So, if you want to monitor the variable, as I told you, temperature, speed, height, pressure, and something like this, you should use X bar chart and R chart. And then select your sample size and then observation. Observe it or monitor it. Using the P chart. Observations are attributes that can be categorized in two stages. We deal with fraction, proportion, or percent defective, fraction defective. Have several samples, each with many observations. So, if you want to deal with the number of defective, you can use the P chart, but you should calculate the fraction defective, not number of defective, fraction defective. Then you calculate the fraction of defective. Fraction of defective, I told you how you should calculate the number of defective divided by number of sampling, number of whole samples. For example, I told you in the company the number of defective was 80, and they repeat the sampling for 20 hours. For example, for 20 times. In each time, they selected 100 unique products. So, 20 multiplied 100 gives you 2000. The whole sample size for 20 hours. The number of defective divided by whole gives you P bar. And number of defective in each hour divided by sample size in that hour gives you fraction defective that we calculated for each hour in hour number 1, hour number 2, hour number 3 until hour number 20, sorry. And using a C chart. In using C chart, as I told you, it gives you the number of defective. Number of defective should be directly calculated and should be directly used in formula. No fraction defective. The number of defective. Defects such as the number of blemishes on a desk, number of tubes in a page of text, and flaws in a bolt of clothes. They are the example in any company, manufacturing company. Okay. Now we want to talk about an important part of the chapter. If you remember, I told you if all of the spots or all of the dots has fallen inside the control area that is between UCL and LCL, you can tell the process is under control. But even one point has fall out its area, you can tell the process is not under control. Okay, now I want to modify a little of my remarks. Now I want to tell you if all of the dots fall inside the area, we cannot tell the process is under control. Listen carefully and don't confuse with two sentences. I want to tell two sentences now. Okay, the first sentence. If even one point fall outside the area, you can tell the process is not under control. Sentence 2. If all of the dots fall inside the area, we cannot tell the process is under control or not under control. Listen carefully. You may be okay. Do you understand? I repeat again because it's very important. Listen carefully. If even one point falls outside the area, you can tell the process is not under control. But if all of the dots fall inside the area, the process may be not be under control. How we should understand it, and how we should tell when the process is under control, when all of the dots have fall, or all of the data have fall inside the area. Now let's check some patterns together. When you face this pattern that you see on the screen, it is called normal behavior. In this pattern, process is in control. Okay, we have upper control limit, we have lower control limit, we have mean. All of the dots have this behavior, so the process is in control. But look at this. One plot out above or in below. In this behavior, we can tell the process is not under control or is out of control, because one point is out of area. Here, all of the spots have fallen inside the area, but the process is not under control. Despite all of the spots have fall inside, but we should tell the process is not under control because we have current here, upward current or onward current. Sorry, downward current. Because in this behavior, we can tell in the future one of the plot or one of the dots will be outside because we have current, upward current, we have downward current. It causes the operation manager are worried about the future of process, become worried about or become concerned about the future of, because this behavior is trend upward or downward. Okay, that is true. That is true that all plots or all dots have fallen inside the area, but because we have current, it can make us concerned about future because we can suspect that in the future one of the spots will be out of the control. When you face this behavior, you can tell the process may going to out of control. Another pattern, another behavior. When some of the plots or some of the spots are very near to lower control limit or upper control limit, if the most of the spots or most of dots are very near to line up lower control limit or upper control limit, no difference, it can make the operation manager's concern or it can make worry about the future. So operation managers will be worried or will be concerned when they face this pattern. So when you face that this situation, that most of the spots are very near to upper control limit line or lower control limit line, you should stop the process. This pattern also makes all of the operation managers worry about the future. Okay, in this behavior, when the most of spots are above the target line means X bar bar, R bar, P bar, C bar. The target line means X bar bar in X bar chart, R bar in R chart, P bar in P chart, and C bar in C chart. The target is exactly in middle of UCL and LCL. When you calculate P bar, C bar, X bar bar, and R bar, and when you zero the line of this variable, you can see that this line is exactly in middle of the UCL and LCL. It's called the target. When the most of spots, the number of spots in above the target is much more than the number of spots in under target, it makes the operation manager worry about the future. Here we have 8 spots. The 6th spot is above target and only 2 spots is under target. So it also has a little problem. This is erratic behavior. At first, some of the spots are very near to upper control limit. And also there is a erratic behavior here. Sometimes go increase and sometimes decrease. This erratic behavior also makes problems. And also when you face this pattern, yes, exactly. When the most of points are above target or the most of points are lower the target, we should investigate the process. Exactly, very good. So please let me repeat again. Yes, very. When you face the charts that only even one point is outside the area, you can tell the process is not under control. But when all of the spots have fallen inside the area, you should see the pattern. I told you some patterns that tell us the process may go wrong in the future, or the process may will face problem on the future. For example, when you face this pattern, erratic pattern behavior, you can see the process may be under control. When you see this pattern, the most of the spot or most of the plots are above target. The number of the plot above target is much more than the number of targets and number of the spot is under target, or vice versa. When the most of the plots are under target, no difference. When the most of plots are very near to lower control limit or upper control limit. Also, this behavior can tell you should be careful about the future. And when you face the target, the trend, the upward trend or downward trend, when your chart, your graph is increasing or your graph is decreasing, it also may make problem for you. When the one point is out of the outside, you can tell it's out of control. There is no doubt here. This is a normal behavior. If you see, there is no plot near to line. The number of the spot, the above target and below target is nearly the same. There is no erratic behavior, and this is normal behavior. The process is under control in this behavior. Okay? Any question? Yes. I think it was very nice chapter. What's your idea? Do you understand this chapter? Do you understand this chapter? Um, what do you mean? You can ask your question for everybody, okay, for everybody, not privately, because some of the questions are very good and very nice, and I want to recommend you when you write the question, please write it for everyone, not privately. For example, one of the students has asked, if 40% of the dots are near to target, what shall we call? It means that the 50, when the 40, only 45% of dots are near to target, and the rest of them are near to upper control limit or lower control limit, is not under control. Okay, it's not under control. When the 9 dots out of 20 is only near to target, it means that the 11 dots are near to upper control limit and lower control limit. That's right. So the process is not under control. Okay. I wanted I wanted to solve some example for you today, but I decided to finish the chapter because I thought we have not enough time, and this chapter is very important. So I was scared. I was scared to not complete the chapter. So I decided to finish the chapter at first, and then the next week I want to give more examples just about this chapter. Okay. For example, we will solve two examples, three examples together for all charts: X bar chart, C chart, P chart. I think the doing more example can help you for better understanding. So I decided to finish all of the charts together, and please study the formula for each chart. Okay, and then the next week, because the difficult chapter, it was a difficult chapter, okay, and the difficult chapter finished. The rest of chapter, I think the two chapter has remained. The two chapter is very easy, and we can study together it easily. But I want to spend the more time for solving more example for this chapter. Yes, I send you email this week by Friday. Okay, I give you email by Friday, and I give you some example. I give you some example. Look at the example and try to solve them by your own at home. Next week we solve the example together, and you can ask your question and discuss more about the example for all of the charts: X bar chart, P chart, C chart, R chart together. Yes. The next week I'm going to give more example about this chapter. Yes, sure. We have some practical example next week together. Okay, so we discuss about more example next week together, and you can ask your uh, problems about this chapter, and we can discuss together. And I like to, and I expect you to participate in class and discuss, because as I told you, it has more score, more mark for final. And don't neglect your final project. Have you started it? You have not enough time. Have you formed your group? Please do that as soon as possible. Please form your group together and start to study on project. Okay? Don't neglect the final project. I have sent email earlier to you, and I told you the subject. You should select one of the subject and start your final project in a group, 3 or 4 together. Start as soon as possible. You have not enough time. This semester is going to finish. I think only 2 weeks or 3 weeks has remained. Okay. What do you mean, Mr. Mumin? Dr. Mumin, what do you mean about by which way? Okay. You can search the Worldwide Science in Facebook and find the page of Worldwide Science in Facebook, and you can share your information and something like this, and you can be familiarized with each other through this page and make your group. Okay, you can search the Worldwide Science group in Facebook. Okay, class has finished, and I wish you have a nice time with your family and have a nice time. Okay, I will. Okay, have a nice time with your family. Have a nice night, and uh, Goodbye, everybody. See you next week. Okay, goodbye, everybody.